All right. Well, I got the streaming, set up. It's already streaming. It's 9 o'clock already, so I'm gonna get started. Are there any questions about the homework assignment? The carry look ahead atom. Yes.
So is there going to be some propagation of like the E going through there, or is it?
Yeah, there'll be some propagation, because I can show you a kind of how everything relates. So the x and the y, are x, y, and also k0. These are the input pins. So the first thing you need to do is to figure out, okay, what are the p and what are the q's? Okay. So from the p's and the q's and also k0, then you can figure out what is k1, k2, and k3 in this case. From k1, k2, and k0 itself, combined with the x and the y, then you can figure out what is S0, S1, and S2. So yes, so you would have to experience at least 1, 2, 3 levels of gates. So 3 levels of gates would be normal. But the point about the carry look ahead mechanism is it doesn't depend on the previous carry. So whether you're calculating your K100 or K1, it is still 3 levels of gates. As opposed to the other mechanism, which is carry ripple, then K100 will take 100 or 99 propagations through the adders, as opposed to K1, which will only take 1 propagation delay. So this one is constant, regardless of how big your app is. Okay. So that's a good question. Any other questions related to the homework assignment? No questions. Okay. I do have to warn you that I have to end today's lab a little bit early, because the San Juan School District, has a minimum day today at the middle school that my son goes to. So he's out way earlier than usual, so I have to go pick him up, at that time. All right. So what we'll do today is we will continue with our topics, but today we're going to move into something that is sort of related to adding and subtracting, and sort of not. So we'll go ahead and take a look at that particular topic. So let me start up the web browser first. Go to Canvas, and then we'll go from there. So Canvas, and sign in. Okay. And I think this is the 13042. There we go. Okay, so I added one more slide. Oh, this is the wrong class. That's 440. 310. Okay, I think it's this one. There we go. All right, so I added one more slide to the modules. So when you check out the modules, there's one more that talks about signed value representation. Okay, so before we talk about signed value representation, I'm just going to go back to subtraction and do one single subtraction that will kind of help start on this particular topic. All right? Okay, so let's go ahead and look at this one subtraction. I'm going to use the documents camera. So this way everything that I do on paper is going to be recorded. I still have not figured out how to use this Elmo device. It's a TT12 Elmo device. I'm not sure how it's hooked up. I think it's hooked up to USB, so I should be able to use it as long as there's a driver. But apparently not yet.
Professor?
Yeah?
Did you already do a mic check?
Do a mic check?
Did you already do one?
I thought I did, but let's double check. Yep. Okay. So the mic is going, the streaming is going, so that's good. Good. Always good to double check. Thank you. Let me start VLC one more time and see whether it's hooking up or not, because this is connected. So we'll start one more time. Capture device. Video 0, play. There we go. Okay, excellent. And I'll get it all focused. There you go. All right, so we'll go ahead and do one single subtraction, and I'm going to use this as a starting point of today's topic. So we'll go ahead and start with this one, 0, 0, 0, 0 minus 0, 0, 0, 1. Okay, no big surprises, okay, because we kind of talked about subtraction already. So we'll go ahead, and I'm going to label the rows. This is row Q. This is row T corresponding to the lecture notes. So just so that when you go back to the lecture notes, you can find the correlation between what I talk about in class and also the notes. Carry in or borrow in this case can be assumed to be 0 because I'm just interested in 0 minus 1. That's all I'm doing. So using this the same method that we do addition, 0 minus 1 is a 1. But that is contributing a borrow already, so we have a borrow of 1. 1 minus 0 is a 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. 0 minus 0 is a 0. 0 minus 1 is 1 with an overall borrow. Okay, so this is just mechanically using the gates that we have talked about. This is how subtraction is going to occur when you have 0, 0, 0, 0 minus 0, 0, 0, 1. And the result is 1, 1, 1, 1. Okay? Does that make sense? It makes perfect sense. It makes perfect sense because you have an overall borrow. Okay? In other words, I'm asking you and say you have no money in your pocket, and I say, okay, can you give me $1? You go like, no, I don't have $1, but I can borrow, right? So you basically, the only borrow you can do here, the overall borrow, is this bit here. So you're borrowing a quantity of 16, and you're giving me 1. So what do you have left? 15, right? And that's 1, 1, 1, 1. So it makes perfect sense. Okay, it makes perfect sense from that perspective. But then we have a problem because now we are saying 0 minus 1 is 15. Because 1, 1, 1, 1 is 15. But at the same time, we know that 0 minus 1 is supposed to be negative 1. Okay, so we have a little bit of a confusion here. So the next thing we wanted to do is to take a look at the number line. Okay, so we'll start with the number line. You guys already are familiar with the number line concept. So you start with 0, you have 1, 2 on one side, and then you have negative 1, negative 2 on the other side. Theoretically speaking, in terms of integers, the number line goes indefinitely in both directions. There's no such thing as the maximum integer, nor such a thing called the minimum integer. Because if you claim that x is the maximum integer, then I'll ask you what is x plus 1? Which is 1 larger than, quote unquote, the largest integer, which makes the largest integer not the largest integer. Okay, so that's theoretical. In a math class, that's what your professor is going to tell you in a math class. But in a programming class, that is not the case. Okay, the int type in just about any practical programming language has a range because we only allocate a certain number of bits to represent values. So in C and C++, when you say int, usually it means 32-bit. When you say long, it means 64-bit. When you say long, I think that is still 64-bit. Okay, there might be a way to use a 128-bit integer, but nonetheless, it is fixed. Okay, there's a certain width to it. So when you think about that, okay, so if I want to confine the program, if I want to restrict the program to only use 4-bit integers, then you have to think about, okay, I know there's a maximum integer that can represent here, and also there's a minimum value on the negative side. Okay, that seems to make sense, right? Because with 4 bits, you only have up to 16 unique bit patterns. With only 16 unique bit patterns, you can only represent 16 different values. Pick those 16, okay? But it's finite, okay? All right, so we'll go ahead and start on the next page. And this one is going to be kind of important. So instead of looking at numbers or values in a line that is linear, I'm going to turn it into a circle. Okay, so now we have a circle. And it's our number line, but it is wrapping around because with a finite number of bits, there are only so many values we can represent. So we'll start with something that is obvious, the value of 0. Okay, with only 4 bits, how would you represent the value of 0? What would be the most natural way to do it? 0, 0, 0, 0. Okay, that makes sense to me. Okay, all right. So I'm going to put up all the slots first. So we have 16 slots, or 16 places. What about 1? The value of 1 should be represented by
0, 0, 0, 1.
0, 0, 0, 1 would be a good one. Yep, okay, I can take that. What about 2? That's a tricky one. In base 2, 0, 0, 1, 0. Okay, because it has 1 of 2 to the power of 1. Okay. What about 3? Okay, 4 is
0, 1, 0, 0.
Yep. And so on. So we got this down. Okay, that's not too bad. Okay. And I'm not going to fill up the next one. Instead, I'm going to go back to 0 and then go backwards. Okay? Well, okay, never mind. I'll do it this way. What about this one?
8.
It's 1 after 7, so it's naturally 8. And then we got 9, 10, 11. Okay. You don't have to copy this. 13, 14, and finally we got 15. Okay, so if you want to associate each bit pattern with a non-negative value, unsigned value, it can go from 0 to 15. Woohoo! But if you want your integer to represent, let's say, the net worth of someone, that might go negative. Okay, so you need to somehow be able to represent negative values. How are we going to do that?
2's complement. 2's complement.
We need to use 2's complement. But what is the natural way of looking at this wheel and go like, okay, we need to figure out how to represent negative values. So what do you think is a natural representation of negative 1? Given that we want to keep the same adder and the same subtractor design that we already have talked about. So I want the same adder and the same subtractor to deal with negative values as well.
It would look like 15.
Okay, so the bit pattern 1, 1, 1, 1 seems like this is a good place to represent negative 1. Why? Why do you think that's a natural place to put a negative 1?
Backwards. Because you can go back.
Go ahead.
Oh, you're just going counterclockwise.
Exactly,
Going the other way.
because going clockwise is to increase the value, going counterclockwise is to decrease the value. So when you decrease the value by 1 from 0, hey, whatever is here should represent negative 1. And this is negative 2, negative 3, negative 4, negative 5, negative 6, and negative 7, and finally negative 8. Okay. Are you guys okay with this? Yep.
This is a 4-bit system.
It's a 4-bit system because I
higher
don't.
up, it wouldn't be at 15, it would be at another number.
Sorry.
Say, I don't know, say it was like an 8-bit system.
If it was an 8-bit system, it was so negative 1 would still be next to 0.
I mean,
But the bit pattern is not going to be 1, 1, 1, 1. It will be 1, 1, 1, 1,
Yeah.
1, 1, 1, 1.
Right.
Okay, but the same idea. Okay, the same idea. Negative 1 is right next to 0. It's on its left-hand side. Okay. So, are there any questions about this wheel? Yep.
Would it be able to deal with like subtracting negative numbers, or then
Yeah, sure. We can do subtracting negative numbers. Okay, let me show you how this works. Really, really well. Okay, so we'll go ahead and figure out. Okay, give me one example that involves the subtraction of a negative number.
5 minus 7?
5 minus 7. But remember, we want to subtract a negative number.
Oh, 5 minus negative 7.
5 minus negative 7, but the sum
be too big.
cannot be represented, in this wheel. So, so pick out one of the things that can be represented here, or here.
2 minus negative 3.
Okay, let's do that. 2 minus negative 3. Okay, so in decimal, we know how to do this already. What is the correct result? 5. Okay, yeah, we know that one. Okay, cool. So now we want to do it in binary. So we look at the table, go like, okay, what is 2? 2 is 0, 0, 1, 0. Okay, 0, 0, 1, 0. And what is negative 3? Negative 3 is over here. It has a representation of 1, 1, 0, 1. Oops, let me move it a little bit like that. Okay, 1, 1, 0, 1. Okay, another example of carrying out a binary subtraction. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 1 minus 0 is a 1. 1 minus 1 is a 0. We don't have any borrow from the next one. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 0 minus 1 is a 1 with a borrow. 1 minus 1 is a 0. Okay. Well, it's 0, 1, 0, 1. Okay, because when you do subtraction or addition, you have to only look at the number of bits that we can deal with. In this case, 4 bits. So we have 0, 0, 1, 0, which is a bit pattern, minus 1, 1, 0, 1, which is another bit pattern. Using the circuitry that we have talked about, it gives us a result of 0, 1, 0, 1. But when you look at 0, 1, 0, 1, it does represent the value of 5. So it worked. Which is weird, right? And I'm kind of surprised that nobody asked me about, well, but this looks really confusing. So let me just pick one bit pattern. So is 1, 1, 0, 0 really representing 12, or is it really representing negative 4? I'm surprised that nobody asked the question.
I was thinking about it.
Sorry?
I was thinking about it.
That's going to
You
depend
were,
on where
okay.
you start.
Sorry, go
And
ahead.
it kind of just depend on where you start. And you have
Okay.
to have some sort of frame of reference for what are we talking about.
All right, that's kind of a good answer. Yep.
Does it have to do with signed and unsigned?
This has to do with signed versus the unsigned interpretation of a bit pattern. But nonetheless, you still have a choice, right? You can choose to look at 1, 1, 0, 0 as negative 4, as the value it is representing, or you can choose to look at 1, 1, 0, 0 as 12, which is the value it is representing. It can represent 2 different values. How do you know which one? So the quickest and easiest answer is, what do you care? Okay? What do you care? In other words, why do you need to know? If it works in both cases, with addition and subtraction, what do you care?
Because we chose it to represent a decimal number.
But it works out in both cases. Yep.
I was going to ask, do we do anything with the leftover borrow number, or is it just...
No, it's just hanging out there. It's useless. For the purpose of this calculation, it is useless. Okay, so what I'm saying is, I don't really care whether, for each one of these bits, whether it's representing negative 3 or 13 in this case. As long as addition still works, as long as subtraction still works, I don't need to know. Is that working out okay with you?
For the bit
No.
calculation, right? For the bit calculation, you don't need to know. But
Right.
the outside result, you want to know.
Okay, let's try another one. Okay, let's try this one. So 1, 1, 1, 1 minus 0, 0, 1, 1. Okay, so we'll try this one. So when you just carry out the binary subtraction, okay, that's pretty easy. This one is an easy one, right? I don't even need a row for the borrow. So that's 0, 0, 1, 1 like that. No overall borrow. But the bottom line is 1, 1, 1, 1 minus 0, 0, 1, 1 is 1, 1, 0, 0. Yep.
Is the difference like the borrow, like how you had the borrow and the subtraction, but let's say you added it, then it would be the result of something different? Like the 3, negative 3 and the 13 is like if you utilize that borrow or not?
No, neither needs to know about the borrow. Okay, but let us take a look at this case here. Okay, 1, 1, 1, 1 as a bit pattern minus 0, 0, 1, 1 as a bit pattern has a result of 1, 1, 0, 0 as a bit pattern. But my question is, well, do we really care about whether 1, 1, 1, 1 is negative 1 or whether it's 15? We don't. Okay, because it works out in both cases. If you look at 1, 1, 1, 1 as negative 1, negative 1 minus 3 is negative 4. Is 1100 representing -4? Yep. Okay, fine. What if you look at 1111 as 15? 15 minus 3 is 12. Is 1100 also representing 12?
Yes.
Yes. So what do you care? It doesn't really matter whether it is representing -3, -4, or 12, because 1100 is the correct in both cases. There's only one case where you really care. It is when you compare. Okay? So I'm going to use another one. This one is going to be useful, so I'll keep this one on the side because we'll have to go back to that occasionally. Okay, so if I ask you, is the bit pattern 0000 in base 2, is it less than 1111 in base 2? That, at this point, you kind of have to think about it. Because if 1111 is representing -1, then the answer is no, it is false. On the other hand, if 1111 is representing 15, then the answer is yes, it is true. So when you are programming in cisp310 using your integers, your signed versus unsigned integers, when you're doing calculations like auto increment, auto decrement, adding the values and whatnot, it doesn't even matter whether it is signed or not. It is only when you compare those values in a condition, then it matters. Is that okay? So we are going to defer the discussion of comparison later. Okay, so let's not worry about comparisons. And at this point, I really am only interested in one thing. How do I get the representation of a value, of the arithmetic negation of a value? That's my only concern for the rest of this lecture. Okay, so you give me a value, give me the binary bit pattern of a particular value signed, and the question is, how do I come up with the binary representation of the arithmetic negation of the same value? Okay, I'll give you a solid, concrete example. Okay, let's say you give me 3. Okay, the negation of 3 is -3, right? So now I know 3 has a representation of 0011. So now the question is, what is the representation of -3? How do I calculate the binary representation of the arithmetic negation of 3? That's my question. So this is the question that I'm going to answer for the entire lecture today. Is that okay? So the first thing we do is we look up the table, see if we can get some clues. So we look up this table, or circle, wheel, okay? So do you notice anything that is kind of, hey, I notice that is true for all of the values that can both be interpreted negative or positive?
They're equidistant from 0, right? Like they're negative counterparts on the same distance away.
You're talking about when you, so 15 minus -1 is 16. 14 minus -2 is 16. Do you notice that? Okay, so when you subtract the negative value from the non-negative value, they all come up to 16. Yep.
Could you say it's not 3 plus 1?
Well, it boils down to that. But we want to find out why that works, right? So you look at 9 and -7. 9 minus -7 is 16. 10 minus -6 is 16. So we notice that particular pattern. Is it coincidental, or does it have to do with how we assign the values? It has to do with how we assign the values. It makes perfect sense, because let's just pick one, in this case. So let's just pick, 10 versus -6. Okay, how do we know this is 10? Because we count clockwise 10 times. Okay, that's how we get to the value of 10, which is the unsigned representation of this bit pattern. How do we get to -6? We also start from 0, but this time we count counterclockwise. 1, 2, 3, 4, 5, 6. In other words, when you add up how much we go in clockwise to get to that point, and how much we go counterclockwise to go to exactly the same point, they should come up to the total number of slots on the wheel. Is that making any sense? Yeah, go ahead.
So, I mean, could you relate it to like coterminal angles?
Sort of, yeah, but it's actually easier than that, right?
Like
It's actually
180
simpler.
degrees is the same as negative 180.
Right, but it's actually simpler than that. It really is just counting. So you have a circle, okay? As long as this is a closed path, this reasoning works. So you have a particular starting point, okay? And you just choose any point within this closed path. Let's say here, okay? I'm not even talking about binary numbers or whatnot, okay? But when you add up how much distance you have to travel clockwise to get here, and how much distance you have to travel counterclockwise from the starting point to get here, when you add up those two distances, what do you get?
The whole distance.
The whole circumference, right? What if I pick another spot? What if I pick this spot here? Would that property hold?
Yes.
If you add up the distance from the starting point going counterclockwise to the distance to get to the same point in a clockwise fashion, would it still add up to the same?
Yes.
They have to add up to the same. That is the reason. So getting back to our example here, because the entire circle has a distance of 16, so when you add up the distance from 0 going clockwise to a particular point, and you add up the distance from 0 going counterclockwise to exactly the same point, they have to add up to 16. Is that okay? But that's really useful, because now I can go to I can try to make a general equation now, because now I can say, oh, you know what, 16 minus x being a 4-bit pattern, is the representation that we need to represent negative x. Is that making any sense? Let me say that one more time. So x is the 4-bit representation of a value v. Okay, so x is a bit pattern, x is an actual value. Is that okay? So x is always like 4 bits, but v can be -1, v can be 5, v can be -8, can be +4, and so on. So I'm completely separating the concept of a value from the representation itself. Is that okay? All right. So what I'm claiming here is the bit pattern of 16 minus v is the representation of negative, or the negation, arithmetic negation of v. That's what I'm claiming. So let's look at this statement here and make sure that we understand what it is talking about. So I'll give some concrete values, okay? So let's say v is -3, okay? So I'm going to use it up here. So let's say v is -3. That won't work. This has to be the x here, sorry. So it has to be the binary subtraction of x from 16, which is 1, 0, 0, 0. There we go. Okay, but this will work because when v is -3, what is x? What is the binary representation of -3? Well, you don't have to do any calculation. Just look it up. 1, 1, 0, 1. Okay, so we'll put it here. X is 1, 1, 0, 1 in base 2. Is that okay? Because v is the actual value, which is -3, but x is the binary pattern representing that value based on that wheel. Is that okay? So now we say, okay, what about the negation of -3? What is the arithmetic negation of -3? Just 3 itself, right? So we want to see whether this works or not. So now we do this calculation, we have 1 followed by 4 zeros minus the representation of -3, which is 1, 1, 0, 1. And we got a, okay, this, we'll make a long subtraction here. Oh, okay, you can see that. Okay. 0 minus 1 is 1 with a borrow. 1 minus 0 is a 1, 0 minus 0 is a 0, 0 minus 1 is a 1 with a borrow, 0 minus 1 is 1 with a borrow, 1 minus 1 is a 0, 0 minus 1 is a 1 with a borrow, 1 minus 1 is a 0, and we have a leftover 1 over here, which, you know, I have no place to put, okay, because I need to focus on just 4 bits. So the question is 0, 0, 1, 1 the binary representation of the arithmetic negation of -3? That's a long one. The answer is yes, that works. Okay, but we have one slight problem here. We can't really use a 5-bit number when your processor is a 4-bit processor. So that whole thing about 1 followed by 4, 0, even though it's really handy and that's what we want to do, you can't do it that way because, you know, we just don't have the 5 bits in order to do this. So what we're going to do is we'll play a trick. Okay, so what we really want to do, okay, is we say, you know, we want to deal with 16 minus x, which is a bit pattern. Okay, which is 1 followed by 4 zeros in base 2 minus x, which is a bit pattern, 4-bit pattern. And then we say, but we cannot do this. We cannot represent 1 followed by 4 zeros because my processor is a 4-bit processor. Okay, every integer can only be up to 4-bit wide. It cannot have a 5-bit integer. So I do this trick here. Because 1 followed by 4 zeros is nothing more than just, you know, 1, 1, 1, 1 plus 1. Is that okay? I can represent 1, 1, 1, 1 is a 4-bit number. I can represent 1, which is 0, 0, 0, 1, which is also a 4-bit number. I don't have a problem with that, right? Okay. But because addition is commutative, I can also do something like this, 1, 1, 1, 1 minus x, which is a bit pattern, and then I add the 1 after the subtraction. Is that okay with you? So, you know, in one single step, I just applied the commutative property of addition and also associative property of addition. So I can put, you know, parentheses around that portion. Is that okay? Okay. So here comes the fun part. The fun part is look at this and go like, I'm going to turn this part into tilde x and then just plus 1. So now we have a big question. What is that tilde x? How many people learned about this operator in cisp310? Nobody. Okay.
Flips the bits.
It flips all the bits, exactly. So the negate, this is a bitwise knot of a bit pattern. Okay, the tilde x is a bitwise knot of a bit pattern. What do we mean by a bitwise knot? Okay, so let's take a look at a bitwise knot operation. So let's just say that x has the individual bits of x3, x2, x1, and x0. So all of these, I'm just spelling out the individual bits of a 4-bit pattern. Is that okay? All right. The negation, or the bitwise knot of x, is nothing more than just the negation of this bit, the negation of this bit, the negation of this bit, and the negation of this bit. So you take each individual bit, you flip a 0 into a 1, you flip a 1 into a 0. That's all. That is all it's going to do. Give you one example. The bitwise knot of 0, 0, 1, 0 is 1, 1, 0, 1, because you have this 0 turning into this 1, this 0 turning into this 1 turning into that 0, and this 0 turning into that 1. Yep. Oh, sorry about that. There we go. I have to change the my little documents camera to make it wide enough to capture the entire sheet, and they can't do that. I'll figure out a way. Is that okay? Bitwise knot? Okay, so once we know what bitwise knot is, what makes this possible? why is 1111 in base 2 minus x the same thing as a bitwise not? Sorry, yeah, this only goes here. 1111 in base 2 minus x is the same thing as bitwise not. How does that work? So in order to see how this works, you have to spell it out. So you have 1111 minus x3, x2, x1, x0. Right? That's the actual subtraction. What is the result of the subtraction? Do we have any borrows in this case? No, we don't have any borrows. So that means whatever goes here is just 1 minus x0. Whatever goes here is 1 minus x1, 1 minus x2, 1 minus x3. Is that okay? But if it's x0 all the way up to x3, each one can only be a 0 or 1. What is 1 minus that bit?
The opposite.
It's the opposite, it's the negation. So we are performing a bitwise not using a subtraction. Is that okay or not? So far so good? All right. So that is the final form. Okay, so when we take this one, then we say, you know, this is also known as 1's complement of x plus 1. Bitwise not is also known as 1's complement. That's just the definition. Is that okay? And what we want to do is also known as the 2's complement, C2 of x. So C2 of x is 2's complement, is defined to be 1's complement of x, which is bitwise not, plus 1. Are we doing okay so far with the definition of the operation? You flip all the bits, you add 1, that's 2's complement. So mechanically speaking, it's not that difficult, okay? Because all you're doing is flipping all the bits and then add 1. But the big question is that really the same thing as arithmetic negation? That is something that we want to find out because, you know, it seems way too convenient. Can someone tell me something about the properties of arithmetic negation? Just a few. So arithmetic negation, you know, we know that, you know, in terms of notation, just as a negation of x, right? So what is so special about arithmetic negation?
You can re-negate it. And you can make the negation of that and become a positive.
It becomes x again, not necessarily positive, because if x is negative to begin with, you get x back, okay? So we just get x back, okay? So what you're talking about is something like this. Should be just x. Yes? Okay? So if I claim that 2's complement is doing the same thing as arithmetic negation, it should have the same properties. Yes? Okay, so let's see. So C2 of C2, oops, C2 of C2 of x should be x. But it's a question mark because we want to show that it is actually x. So we'll try some concrete values first, okay? What do you want to use for x? Just as an example. Pick anything out of the wheel. I'm gonna put the wheel back on so that you guys can choose. And you don't have to choose wisely.
0, 1, 0, 0.
0, 1, 0, 0, which is 4, right? Okay, very good. So we'll start with that. So we say, what is C2 of C2 of 0, 1, 0, 0? Okay, so we'll work on this one step at a time. This becomes C2 of C1 of the same bit pattern plus 1. Is that okay? I'm just expanding the C2 in the middle, in the center. So that becomes C2 of 1, 0, 1, 1 plus 1, right? Because C1 is just bitwise not. We turn all the zeros into ones. We turn all the ones into zeros. Okay. And after you perform the addition, you get 1, 1, 0, 0. Is that making any sense? 1, 0, 1, 1 plus 1 is 1, 1, 0, 0. Now we can check that too using the wheel. Because 1, 0, 1, 1 is 11 plus 1, it becomes 12, and 12 does have the bit pattern of 1100. So it all checks out. So now we perform the 2's complement of 1100, which becomes the 1's complement of 1100 plus 1. 1's complement is to flip all the bits, so it becomes 0011, and then plus 1, and 0011 plus 1 is 0100. Ooh, magically that works. All right. What else? What other operations here do you think arithmetic negation should do? What about taking that? What about taking the arithmetic negation of 0? What do you think is the result? Yes.
Could you go back to the previous page real quick?
Yeah. Yeah. There you go. Yep.
What if you do 8?
Hmm?
What if you do 8?
Now, 8 is not something that you can actually represent. -8 is what you can represent. Because you only choose one, right? You can only either choose the signed representation, which is -8, or you can choose the unsigned representation, which is 8. But 2's complement is working on only signed representation. Okay, so can I take this away?
Yeah.
Yep. Okay. So what about this? Yes? Okay, you got nothing, and if I take away nothing, you still got nothing. Well, that's not exactly what it is, but you're nowhere, and you go in a certain direction. You flip your direction, you're still nowhere. All right, so let's do 2's complement of 000. That becomes the 1's complement of 000 plus 1. 1's complement of 000 is 1111. When you add 1 to 1111, you get 0000. Now, yes, you do have that one extra carry, but that's not a part of the result. Okay, so we don't even take the carry into consideration. So it does work. What else? What about this? What about this whole thing about x minus y is really the same thing as x plus the arithmetic negation of y? Okay, so but this time we need 2 numbers. So I'll let you guys choose 2 numbers, but the sum has to be something on that wheel that makes sense. Okay, so I'll let you guys choose. What do you want your x to be? What do you want your y to be? What is your minuend? It can be positive, can be negative, as long as the sum can still be represented using this wheel, we should be okay. So go ahead and pick something.
-7 and 8.
-7 and 8 will not work because -15 is not on the wheel.
10 and -2.
10 is not, because with all of these ones that have 2 interpretations, you have to choose the signed interpretation. Hmm? 3 minus 5. Okay, so 3 minus 5 would work because 3 only has 1 representation, which is good. 5 only has 1 representation. 3 minus 5 is -2, and -2 is representable using 4 bits. Okay, so 3 minus 5 would work. Okay, so let's go ahead and try that. Okay, so we'll say what is 3 minus 5? Okay, 3 minus 5, and this time we convert everything to 4-bit representation. So now I'm asking, okay, this is the same thing as 0011 plus the 2's complement of 5, which is 0101. Is that okay? So I'm skipping that one step of 3 plus the negation of 5, but that's basically what it is. Is that okay? So the first thing we need to do is to apply the 2's complement to 5. So this is 1's complement of 0101 plus 1. And that becomes 1010 plus 1 because that's just the flip side of it. And now we have 0011 plus 1011. Okay, so you add, I'm going to do it on the side here. 1011 plus 0011. There's a 00 here, 1100. that right? No, I made a mistake. It's 1110. Okay. But 1110 using a sign interpretation, what is it? Let's look at the wheel. This is 1110. The sign interpretation is -2. So we do get the correct result. Okay. This part is binary, this is base 10. So do we have any questions about this part? Yep.
I think I must have missed it when you said it, but why is there not like a negative 9?
Because when you look at the wheel, we want half of it to be non-negative values and half of it to be negative values. So the dividing line is right here. Everything to this side are non-negative values. Everything on this side are negative values. Hmm?
Yeah, why?
Why?
Why is it so like that?
Because because if you don't split it like that, then it becomes asymmetric. Then you have more negative values than you have non-negative values. Yep.
Also for like, for example, number 7, like one would think it could be represented as -9, but there's a 0, the leading number, right? So
Yep.
only if there's a 1 can be represented as a.
So there's a regularity. Yep. So every single value that has a negative every representation that has a negative value that can represent starts with a 1. The most significant bit is a 1. And that turns out to be quite useful. That one single fact that all negative values, the representation of all negative value has the most significant bit being a 1, turns out to be quite useful later on when we need to perform comparisons. Yep.
So if you were to take more bits, like 8 bits instead of 4 bits, would it change? The wheel would change?
The wheel will become bigger, but the pattern does not change.
Okay.
So let's figure it out. Okay, so that's a very good question. So the question is, what is the range given n as the width of an integer? What is the range of values we can represent using the sign interpretation? Okay, I think that's what you're asking. Yep.
Also, will the formula change?
The formula change? Yeah, it will change because instead of using 16, you'll be using something else. Okay, so let's figure out how we can work that out. So I'm gonna use a new page here, and we'll make it abstract. Okay, but we can go back to the other one and cross-check things. So we're basically saying that we have n-bit integers, and they are signed. Okay. But the point is, we have only n bits. So when you have n bits, okay, how many points or how many unique values can you represent in the wheel?
N minus 1.
Say that one more time. N minus 1? No.
2 to the n.
2 to the power of n. Okay, very good. Okay, so we have 2 to the power of n unique values. Now, every time I make a claim like that, the first thing you want to do is to check, okay, did it work for 4? When n equals to 4, did we have 14 unique values? Let's double check, right? Yep, we have 14 unique values on the wheel. Okay? Now, why is this 2 to the power of n? You have n individual bits, and they are independent. In other words, when one bit is a 1, it doesn't affect whether the other bits should be a 1 or a 0. Is that making any sense? So you look at this and go like, okay, this is the least significant bit. How many choices do we have? 2, because it's a bit, right? A binary digit, so it can be either a 0 or 1. What about the next one? It also has two choices. But when you look at the next one, it also has two choices. But when you look at just 3 bits, okay, what is the total number of combinations that they can represent? It's not 6, it is actually 8. Because when the first bit, when the least significant bit is a 1, the other 2 bits can be whatever they want. So you have to use multiplication instead of addition when you're trying to figure out, you know, how many unique patterns that you can store using only 3 bits. The truth table becomes 0, 0, 0, 0, 0 for the most significant bit, 1, 1, 1, 1, and then for the second most significant bit, the one in the middle, can be 0, 0, 1, 1, 0, 0, 1, 1, and the least significant bit is 0, 1, 0, 1, 0, 1, 0, 1, and you can see how this adds up to 8 and not 6. Okay. So getting back to this wheel here, so we have 2 to the power of n unique values. We know 0 is non-negative. What about the most positive value, which is, you know, right here, okay? We want half the wheel to represent non-negative values, right? And we know there is a total of 2 to the power of n unique values. So you go like, oh, okay, how about 2 to the power of n minus 1? You're pretty close. You're off by 1. This is the largest value you can represent. Why are we subtracting 1? Well, the reason is because 0 is taking up 1 spot. Okay, when 0 is taking up 1 spot, then you have to subtract 1. That becomes the last spot that can represent a positive value. Okay, so we'll say, you know, this is the max value you can represent. What about the min value? In other words, if I go backwards, this is -1, -2, -3. What is the most negative value that we can represent? Well, 0 is only represented as a non-negative number, which means for negative numbers, you can really start with -1. So if you start with -1, then the -2 to the power of n minus 1 becomes the most negative value you can represent. So that becomes the range of a n-bit integer. It goes from -2 to the power of -n minus 1 to positive 2 to the power of -1, and then the whole thing minus 1. But we want to double check. Is this what we had when we only have 4 bits? So you plug in n equals to 4, and you ask, n is 4, 4 minus 1 is 3. Was -8 the smallest value we can represent using that wheel? Yes, it was. Was 7 the largest positive value we can represent? Yep, that was the case. So that was a good question. You know, this is the general equation to do that part. Are there any questions about, you know, taking the 2's complement of a particular bit pattern? No questions? Okay, so with the other class, with the Monday Wednesday class, this was the last part of the lecture that relates to signed numbers and also addition and subtraction. And then I moved on and talked about RISC versus CISC architecture. And the lead into that one had to do with comparison. Okay, because as I said, okay, let me dig up the slide that talks about why comparison is kind of important. Because to answer the question of whether 0, 0, 0, 0 as a base 2 number, as a binary bit pattern, is less than 1, 1, 1, 1 as a base 2 binary bit pattern, it depends on the sign interpretation. Are we talking about 1, 1, 1, 1 representing -1, or are we talking about 1, 1, 1, 1 representing 15? Because depending on which way it is, the answer is different in this case. Okay, so then in the other class, in the Monday Wednesday class, I went on and talked about how you don't need all the comparison operators. So we'll go ahead and list all the comparison operators. We have less than, greater than, less than or equal to, greater than or equal to, and also not equal to. These are the 6 comparison operators that you can perform in C and C++. Are there any questions about this? Okay, so here's a question. Can we have more than these 6 comparison operators? Does anyone program in PHP? In PHP, yes, you can have actually more than 6 comparison operators. And you might ask, it doesn't make any sense, okay? These 6 really should represent everything that we can do to compare something with something else. How can there be more than this? Well, in PHP, they have this particular operator, 3 equal symbols. The reason why they have something like that is because PHP is a scripting language, unlike C and C++, which is compiled, okay? As a compiled programming language, C and C++ are also known as strongly typed programming languages. You cannot compare a string with an integer. The compiler will complain and say that these are incompatible types. One is a char pointer, the other one is an integer. They cannot be compared. But in PHP, you can. So now the question is, so what is it going to do when one side is a string and the other side is an integer? It doesn't compare the address of the string. It would actually convert the string, assuming it is a base 10 number, into a numerical value, and then compare the numerical value to the other numerical value. So it would go through an implicit conversion or type change in order to perform the comparison. And PHP naturally does that with a normal equal equal. Now, if you say, I don't want to do any type of conversion, I want both sides to be of exactly the same type and compared as is, do not do any conversion, then you use equal equal equal. Okay? So we don't have to worry about it in this class because we are not dealing with scripting languages. We only have these 6. And then now I claim that you don't need all 6, you just need 1. Okay? If I just give you less than, that's all you need. Is anyone convinced? No? Okay, we'll go ahead and prove it. So we'll say x is less than y is really just the same thing as x is less than y. That is kind of obvious. X is greater than y is the same thing as y is less than x. That's an easy one, right? What about less than or equal to? X is less than or equal to y. If I let you use logical operators, can you get it done? Logical operators like and, or, not, that sort of thing. Can you get it done? It is not the case that y is less than x. Right? And then the next one is just the flip side of this. Okay, x is greater than or equal to y is saying the same thing as it is not the case that x is less than y. Is that okay? Aha! Now we got some stumpers, right? You know, not equal to. We'll deal with not equal to first. X does not equal to y. Now, how can we fix this one? What about this? X is less than y, or y is less than x. Well, once we have not equal to is just a negation of that. So now we have x equals y, being it is not the case that x is less than y or y is less than x. Is that okay? So now you can go back to your C++ class. You know, if you're taking 400 or 430 in the same semester, you can convert your program so you only make use of less than. And then see what your professor is going to say about that. You can just say that, well, the text said that your less than is more than enough to deal with all the other comparisons, and I'm going to show you how. Now, of course, if you want to push this to the extreme, you would also do a pound define, you know, and or use, you know, I wouldn't use another operator because operator overload can be a little bit dangerous in this case. But I would do a pound define like this. Okay, pound define NAND xy to be the negation of x and y. Now, in this case, you have to be careful. I would put extra parentheses around, you know, x and y, just in case x is kind of just so that the operator associativity and priority doesn't get in the way. So remember, NAND can imitate or emulate all of the other operators, right? So your entire program, every single condition, can now be a mixture of NAND and less than. Nothing else. You don't need not, you don't need or, you don't need and, you don't need greater than or equal to, less than or equal to, not equal to, or equal to. Everything boils down to NAND and less than. You will have a lot of parentheses, a lot of nesting, but nonetheless, it is doable. I'm pretty sure your 430 or 400 professor will notice that. It's like, whoa, this is a little bit different. How come your condition spans over 3 lines? But why do you think I bring this up? This class is about assembly language programming. It's about computer architecture as well. So why am I always so concerned about this is the bare minimum? If you have this, you can do all the rest.
The goal is to use the bare minimum, right? We're trying to use the bare minimum, right?
We're trying to use the minimum in hardware. In other words, if I'm designing a processor, instead of having my processor to natively be able to do all the 6 comparisons that we are used to, I'm just going to say, oh, this guy only needs to do 1 single comparison, which is just less than. We can deal with the rest, using these things. Okay, but why am I so concerned about that? What am I going to buy other than bragging right and go like, look at my processor, it only has less than, it can do everything else just using less than. Other than bragging rights, is it really useful? And why is it useful? So keep that thought in your mind right now, and then we'll switch our scene to a different scene, okay? So we'll just say that you guys are having a LAN party. Okay, so somebody's hosting a LAN party, and you're inviting your friends to bring their super duper game desktops over to your house so that you guys can basically have your team in the same room so that you guys don't need to do Discord just to coordinate everything. Okay. So the first thing you need to do is what? You tell your parents that I'm gonna have some friends coming over and we're gonna have a LAN party. Okay. And what is your biggest concern, or what should be your biggest concern at this point?
Parents saying no. Parents saying no.
Your parents say no, but why do you think your parent might say no?
Not enough room.
Not enough room? I'm not too concerned about that. I'm concerned that you guys will trip the circuit breaker. That is my first concern as a parent. Is I don't want your game buddies to trip the circuit breaker. Would it? Is there potential to do that? Let's think about it. So let's say you're playing League of Legends, okay? And how many people how many summoners are on each team? 5, okay. So you got 5 people, including yourself, right? And then you look at all those souped up gaming machines. How much power is each one going to consume?
Like about
1,500 watts.
Well, okay, so let's do some math here. Okay, come on, people. You guys can do some math. Okay. Okay, as a gaming PC, okay, it probably has a dedicated graphics card, right? Dedicated video card. What is the power consumption of a high-end graphics card today? NVIDIA. Let's say we stick with NVIDIA. 250 watts is actually the cap of that. Okay, so you have 250 watts per video card, and there's a technology called SLI. What does that do? You can link multiple, not just 2. You can actually have as many as your motherboard supports, right? Okay, but let's just say that you only have up to $2,000 to spend on the PC, so you can only buy 2 of these cards, right? So now you have 2 of these things, 200 plus 250 watts. Okay, what about the processor itself? Now I know once you have high-end graphics cards, a lot of the rendering is completely completely offloaded to the graphics card. So the main processor really doesn't have that much to do, but you still want to have a reasonably fast processor. Let's say an i7 with quad core, which is not even top of the line anymore, right? So what about the power consumption of that?
Around 100 watts.
Let's say 120 watts, okay? But then you also have hard drives, okay? Because you don't want to lose, all your gaming, your history, all the stuff. So you have backups of backups of backups, and on top of that, you are backing up every single movie that you have ever seen, right? And you don't want to lose that at all. So you have a 5-disc RAID with 2 live, two how do you call those things? It's called a live spare. So that if any drive goes bad, you don't have to run to fries anymore, because the other 2 drives are spare drives, and they're live, they're online all the time, right? So you have no downtime whatsoever. So let's say that's going to take up another 120 watts, which I think is reasonable. Okay, your 5 drives and your motherboard, plus your display, your screen, and also your subwoofer and stuff like that. Okay, so everything add up to about 750 watts, for one single gaming computer. Okay, and remember, you get 5 of these things. So what do you get when you multiply this by 5? Okay, we'll do some quick calculations here. I think it is 3750, right? Close to 4 kilowatts. What is the largest circuit breaker for 110 circuit? Open up the panel, and you see all the amperage, right? Because the circuit breakers are rated by amperage. So the largest one that people use in a household is 30 amp. So 30 amp times 110 volts, which is your line voltage, is 3,300 watts. It's less than what you need in a single room. So you will need to ask your parents to actually have 2 circuit breakers going into your room. Okay, so let's say your parents go like, okay, fine. If you guys are paying for the electrician, we can add another circuit breaker and route another wire from the circuit breaker to your room. Okay, fine. That problem is solved. And then what is the next concern that you might have? Okay, so the question is, with all of these power, where is it going to? And some people might say it's all going to rendering, network traffic, deciphering, and calculation of the positions and stuff like that.
Lighting up the keyboard. Lighting up
the keyboards, yes.
That's a lot.
Yep. So we have all that, right? But 99.999% of this energy is converted into heat.
Yeah.
You cannot destroy energy. You can only convert it, right? So a small portion is converted into light. That would be your monitor, the LEDs, and your fancy spancy, lit up, interior of your computer case, right? But 99.999% is converted into heat. How much heat are we talking about here? What is the power rating of one single hair dryer? You guys don't know? Don't you look at all the appliances that you have in your household and look at all the power consumptions? You don't do that? Okay, so hair dryer. Okay, so we will just look at one and go, oh, Dyson. I didn't know that Dyson makes supersonic hair dryer. Okay, so let's look at the specification. I wouldn't do that with a hair dryer. If you value your eyesight, you may not want to do that. Okay, I want the specification. $400 for a hair dryer.
That's with attachments. It's cheaper without attachments.
But what about the power consumption? I just need the specs.
Technology.
Yeah, that too. Yep. Okay, owners area.
Right on the top. Technology.
Features. Okay, let's check out features.
Why are they wearing backpacks?
She's worried that she spent like $400.
For real?
Oh, come on.
What did I just buy?
No. I need numbers.
So technology.
Specifications. There we go. Power is only 1600 watts. Okay. So if you
Only 1600 watts. Well, I mean, some of these are up to like 1850, which is the maximum of what a 20 amp circuit breaker can do. So this one is only 1600. So when you compare this to the power consumption of your, five, of your LAN party, it comes a little short. Okay, you have to be running 2 of those hair dryers the whole time,
And a little bit more.
and a little bit more. Well, each person is another 200 watts of your thermal output, by the way. Okay, so you have 5 people in the room, so that's another kilowatt of thermal output. So your entire room has close to 5 kilowatts of heat. Okay? Then you might say, well, it's not a big deal. My bathroom is pretty small and I run my hair dryer and nothing seems to heat up too much. Well, that's only because you run your hair dryer for about 5 to 10 minutes. How long is your LAN party gonna last? Until the circuit breaker breaks. Right? Okay, so let's say it's 2 hours. It's the same thing as turning on 2 hair dryers full blown for 2 hours, and then plus some. Okay, I don't think you can cool down your room to the point where you can survive. Is that making any sense? Okay. So getting back to this number here, what do you think is going to be the biggest challenge that Google has when they are putting together these huge data centers for to house the hardware for all the search engines and everything? It's cooling. Okay, it's not getting the power in; it is getting the heat out. That is the limiting factor. That limits how much processing power they can put into a single location. It's how fast you can cool the hardware. Is that okay? Yep.
Why do you think you slow down when you get hot?
Because they would die if you. Because semiconductor only works up to a certain temperature. The hotter you get, the resistance changes. And also, heat also would change, the PN material. They will start to go places where they are not supposed to. So you can permanently kill a semiconductor device when it's exposed to too much heat. That's why your Pentium processor, has an internal thermal protection. At a certain point, it will just shut down itself. It just, okay, no more. Yep. Okay. So what does this have anything to do with the discussion that we just had? Okay, remember the hardware that only knows how to do less than and also NAND, right? What is that going to do to the circuitry? As opposed to another hardware that can do all 6 comparisons, all the logical operators that we are familiar with. What is the difference? One uses more transistors, right? The one that can deal with all the ones that we are familiar with, is going to be consuming, it needs more transistors. But the one that says, okay, I only need to know how to do less than and NAND is going to use fewer transistors. Is that okay? So I don't know why this stopped working. Maybe I jittered the connector too much and it just died. Yep, it has lost the connection to the. It's okay. It's no big deal. So we are looking at RISC, R-I-S-C, versus CISC, CISC. RISC stands for Reduced Instruction Set Computer, and CISC stands for Complex Instruction Set Computer. The approach of using only implementing less than and also NAND, doing the minimalist, is called RISC. So that we are reducing the amount of instructions that are available, and the compiler now has more work to do. Because in order to translate your C code into machine code, it has to translate a little bit more because each instruction doesn't do as much anymore. When you have CISC, which is the Intel i7, i5 platform, you have more instructions, and each instruction can potentially do more, and it maps to what you normally do a little bit better. So the compiler has a quote-unquote easier time, doing the compiler.
So when you look at these two, when you look at the transistors on the cisp processor, they get pretty good utilization. Okay, so if you look at each individual transistor, they go like, oh, they're busy all the time. When you look at the cisp processor, a lot of transistors are not getting used most of the time because it's redundant. There's a lot of redundancy in the cisp processor. So what we really care about these days is not MIPS, MIPS, or whatever unit you want to use. The key part is IPS, instructions per second. Okay, this is back in the good old days when we only measured in million instructions per second, and these days we really should be measuring in billion instructions per second, bits. Okay, that was the holy grail before. Okay, this is what people were sorting after: is we make faster and faster and faster processors, and then people found out that we can't extract the heat. So these days people are changing this from instructions per joule. Okay, now this is a physics unit for energy. 1 joule, Joule, is 1 watt-second. Is a measurement of energy. In other words, now people are measuring how much computation can I do per unit of energy, because that amount of energy is always going out in heat. Is that okay? So we want to be, for each watt converting into heat, I want to get more instructions done. Is that okay? And as it turns out, when the focus is on how much computation done per unit of energy, RISC is going to be the winner. When you look at each RISC processor, you go like, one single clock doesn't do nearly as much as one clock of a cisp processor. But when you look at the energy that it's going to spend on each instruction, you go like, wow, it's actually a good deal. So instead of using a few really high-power cisp processors, the data centers are going the opposite way. They're going for a whole lot more RISC processors. Because in the end, a whole lot of RISC processors turn out to be much more energy efficient compared to a few high-powered cisp processors. So the processor that we are going to use later on in this semester falls into the RISC category. It is a minimalist kind of processor. Well, okay, not entirely minimalist, but it is pretty close to minimalist, as opposed to a cisp processor. So this is the final thought, okay? Is there a place for cisp processors today? Like right now? And why do we still have cisp processors? So you think about it, okay? So let's think about everything that has a processor in it. My Fitbit has a processor, right? My phone has a processor. My Fitbit has a processor. You guys have tablets, they have processors. We have a desktop computer, that has a processor. Well, with a Fitbit or phone, you can probably see why energy efficiency is desirable, right? Because you don't want to lug along, a huge battery on your wrist, which by itself is enough exercise. Here's a lead-acid battery that can last you 5 minutes. So you fill your backpack with spare lead batteries so that you can last the whole day. Okay, so we can understand that. Your cell phone, same thing. Okay, you don't want to have to recharge your phone all day long. So energy efficiency is important as well. Your desktop computer doesn't need to be energy efficient, but if it is energy efficient, it's good. So why are we still using cisp processors on the desktop computer? It doesn't matter to most people, but but why not? I mean, because energy efficiency is always it doesn't hurt, right? It's only going in the positive direction. Yep.
Is it cheaper?
Is this faster? Is this just faster? It has more instructions per second.
It is a little bit faster when you look at only one single processor, but then you can have more RISC processors to make up for the slowness of one single RISC processor. Okay, the answer is Microsoft. What does it have anything to do with Microsoft?
Because
Okay,
what-
I'm using Linux.
Operating system you use cisp?
Yep, the operating system. So the question now is, what platforms supports Linux? Okay, so we'll figure out supported computer architectures, and so here's a list right here. It keeps going and going and going. Okay. Plus some that is probably in a research institute that is not even published here. I would say that's a pretty long list. Yes? What do you think is the list of architectures that can support Windows? What do you think that list would look like?
Smaller.
4, 5, maybe 5 entries at the most. But why is that the case? Why do you think Linux is supported in all of these different architectures? And many of these are not even resembling each other. They're not from the same family. These are like entirely different architectures.
Does Linux use RISC?
Hmm?
Does Linux use RISC?
Some of these are RISC, some of these are cisp. They go all over the place. But what about in the case of Microsoft Windows? Why can't I run Microsoft Windows on a PowerPC platform?
They have licenses and there's money involved.
But Microsoft can just make a version of their operating system that works on the PowerPC platform and sell that license to you too.
Yeah.
I mean, Microsoft has to tell Intel, do not make any changes to the instruction set. We want 100% binary backward compatibility. Why is that important?
Because they've been developing the x86 architecture for a long time, right?
Okay. Then what makes Linux mobile? Why do we have all these other platforms, other architectures supported by Linux? What is the difference? What is the one key difference between the development tool chain of Windows as opposed to the tool chain for Linux? Open source is one, but in terms of the tool, it is the compiler. Okay, so you write the same C code. Okay, you write the same C code regardless of the actual target architecture, because the compiler is the one that is converting your C code into machine code, which is dependent on which architecture you're dealing with. So with GCC, it has a very modular design, which means the back end, which is the part that spits out binary machine code, is entirely separated from the rest of the compiler. So if you were to retarget GCC for a new architecture, it is minimal work. No, when I say minimal work, it means a graduate student working maybe a year or so, but that's one single person working a year. It is not that much time or resources. If you have a compiler that is really hard to retarget what code it spits out, then you have a problem, because you can no longer just say, oh, we'll just recompile the kernel, because your compiler cannot deal with the new architecture. So I think that is the bottleneck of Microsoft. That's why they cannot retarget a new architecture. Okay, so that's the end of today's lecture. Signed numbers, basically just signed value representation for today. I'll see you guys over at the lab, but we have to cut the lab a little short, so I will try to answer questions as quickly as I can when we get to the lab.